Welcome back to the deep dive. You're here because you want to cut through the noise and really grasp reinforcement learning, and you want to do it efficiently.
Yeah, exactly.
Consider this your focused exploration of what matters most in RL, without all the fluff.
Right. We've basically distilled the key findings from recent comprehensive analyses of RL, the core algorithms, methods that work, the essential tools, challenges that stick around, and the really impactful applications we're seeing right now.
We're going beyond just the surface level here.
Totally. Giving you the insights that actually count.
Okay, let's get straight into it then. Reinforcement learning, RL for short, it's about training an agent to make sequences of decisions.
Right, within some kind of environment.
And it learns by getting feedback rewards based on its actions.
Think of it like learning by trial and error, essentially, but aiming for a long-term goal.
Yeah, and it's different from supervised learning, right? No labeled data needed.
Exactly. And it's not quite unsupervised learning either, because there is this reward signal guiding it towards a specific goal.
What seems really powerful is this interactive learning part.
Oh, absolutely. The agent is actively, poking around its environment.
And the results, the consequences of its actions, they directly shape what it does next.
Which makes it just uniquely suited for tackling problems where, well, the best strategy isn't known up front, it has to be discovered through experience.
And this whole interaction, it's often formalized using something called a Markov decision process, or MDP.
Yeah, that's the mathematical backbone, essentially. And MDP gives us a framework for thinking about how the agent moves between states in the environment by taking actions.
All with the aim of getting the most reward over time.
Maximizing that cumulative reward, yep. So our mission for this deep dive is to pull out the really crucial stuff about RL.
Its core ideas, the main algorithms driving things forward,
The tools people actually use, the big hurdles still being tackled.
and where it's making a real difference out in the world. We want to give you those aha moments, focusing on the core insights.
Okay, so fundamentals first. An RL system, you've got the agent that's the decision maker,
Right.
and it operates inside an environment. That's the system it interacts with.
Okay, and the environment has a state.
Exactly. The current situation the agent finds itself in. And from that state, the agent chooses an action from, whatever options are available.
And after the action comes the reward.
Yep. Feedback from the environment. Was that a good move towards the goal or not?
And over time, the agent builds up its strategy, its policy.
That's its learned approach, basically mapping states to the actions it thinks are best in that situation.
So the big picture goal is learn a policy that gets the most total reward.
Exactly. And not just immediate reward, but the maximum expected cumulative reward over the long haul. The MDP framework helps us nail that down mathematically.
Okay, so how do these agents actually do the learning? You mentioned a split, model-free versus model-based algorithms. What's the difference there?
The core distinction is really whether the agent tries to build an explicit model, like an internal understanding of how the environment works.
Okay.
Model-free algorithms learn directly from just trying things out and seeing what happens. They estimate action values or the policy itself without needing to know the environment's underlying rules.
Right, learning what to do without necessarily knowing why it worked.
Precisely.
And within model-free, you've got value-based, policy-based, and actor-critic.
Mm,
Let's maybe start with value-based.
sure. Value-based methods are all about learning a value function. This estimates how good it is to be in a certain state or how good it is to take a specific action in a specific state.
Okay.
Q learning is probably the most famous example. It's off policy, meaning it learns the best possible Q values, the expected future reward, even if it's currently exploring in a suboptimal way.
And it uses a Q table, right?
Yeah.
Like a lookup table for these values.
Traditionally, yes. For simpler problems, it stores these Q values in a table.
So, building a map of goodness for every state action pair. Then came deep Q networks, DQN. That involves deep learning.
Yeah, DQN was a huge leap. Its big advantage is handling really complex environments, like Atari games, straight from the pixel inputs, high-dimensional states.
How does it do that?
It uses a deep neural network to approximate the Q value function instead of using a table.
Ah, so it generalizes.
Exactly. It can estimate values for states it hasn't seen before, which is crucial for anything complex.
Okay, so it learns a function, not just memorizes values. Now, SARSA was mentioned as on policy. How's that different from Q learning?
Right. On policy means the learning updates are based on the policy the agent is currently following. SARSA updates its Q values using the action it actually takes in the next state.
Following its own current strategy.
Yeah, so it can lead to more, let's say, cautious exploration. It's evaluating the path it's actually on. Q learning, being off policy, always looks at the potential best next action, which might be riskier if its value estimates are off.
Okay, that makes sense. SARSA learns from what it actually does. Moving to policy-based methods, they directly tweak the policy itself.
Precisely. Instead of figuring out values first, they directly adjust the policy's parameters to make good actions more likely. Policy gradient algorithms are the foundation here.
How do they work?
They calculate the gradient, the direction of steepest increase of the expected reward with respect to the policy parameters, and then nudge the policy in that direction.
Okay.
This works really well for, say, continuous action spaces, like controlling a robot arm joint angle where value tables are impractical.
So learning a control strategy directly and reinforces a basic one.
Reinforces, yeah, a foundational Monte Carlo policy gradient method. Monte Carlo here means it learns from complete episodes.
The whole sequence of actions.
Right. It updates the policy based on the total reward received at the very end of an episode.
Oh.
It's simple, conceptually, but that reward only comes at the end. So it can be hard to know which specific actions were good or bad along the way, leads to high variance in the learning signal.
Right, the credit assignment problem.
Yeah.
Okay, then there were actor-critic methods. Sounds like a hybrid.
That's exactly what they are. They combine the strengths of both. You have an actor, which is the policy learner.
Decides what to do.
Yep. And a critic, which learns a value function.
Evaluates how well things are going.
Exactly. The critic provides feedback to the actor saying, hey, that state you got into is better, worse than expected, which helps the actor update its policy more efficiently than pure policy gradient methods often can.
So the value function guides the policy learning. What are some big actor-critic algorithms?
Well, an early influential one was asynchronous advantage actor-critic, or A3C. It used multiple agents exploring in parallel
Speeding things up.
and updating a central policy asynchronously. Yeah, much faster training. More recently, proximal policy optimization, PPO, has become super popular.
Why PPO?
It's known for its stability. It uses a clever trick to limit how much the policy can change in each update step. Prevents those big destabilizing jumps in strategy.
Makes sense, so it's reliable.
Very. It's a real workhorse in robotics and gaming. Then there's soft actor critic, SAC.
Soft.
Yeah, it adds an entropy term to the objective. Basically, it encourages the agent to act as randomly as possible while still maximizing reward.
So it explores more broadly.
Exactly. Helps it avoid getting stuck in narrow strategies, especially good for continuous control tasks.
Okay, that's a great rundown of model-free. How do the model-based algorithms compare?
So model-based is different. These algorithms actually try to learn a model of how the environment works.
Like learn the rules of the game.
Kind of, yeah. How states transition, what rewards you get.
Yeah.
Once it has this model, even an approximate one, the agent can use it to plan.
Plan, like simulate potential futures.
Exactly. It can try out sequences of actions in its learned model, its internal simulation, without having to take steps in the real world.
Which could be faster or safer.
Definitely. DynaQ is a classic example. It learns from real experience, and it does planning steps using its learned model to update its values or policy. It gets more bang for its buck from each real interaction.
Interesting. What else?
Monte Carlo Tree Search, MCTS. This one builds a search tree of possible future moves by simulating outcomes.
Like exploring different branches of possibilities.
Precisely. It balances exploring promising branches and exploiting known good ones, famously used in AlphaGo.
Ah, right.
And then there are approaches like world models, which use generative models to learn a compressed representation of the environment. The agent can then plan entirely within this learned dream world almost.
Wow, planning in its imagination. That's pretty cool.
Yeah.
You also mentioned some historical ones, Menace and TD Gammon. Briefly, why were they important?
They were really foundational. Menace, the tic-tac-toe machine made of matchboxes.
Matchboxes. Seriously?
Yeah. It showed very simply this idea of learning from trial and error by changing probabilities, represented by beads in boxes. TD Gammon played backgammon at a world-class level using self-play and temporal difference learning, TD learning.
Okay.
It really demonstrated the power of RL for complex strategic games way back, inspiring a lot of what came later.
So, laying the groundwork. Okay, we've covered a lot of algorithms. Value-based, policy-based, actor-critic, model-based. The choice depends on the problem, clearly.
Absolutely.
Now, to actually use these, people need tools and libraries, right? What are the key ones?
Oh, yeah. The tools are crucial for making progress practical. OpenAI Gym, now often called Gymnasium, is sort of the standard benchmark suite.
For testing algorithms.
Exactly. It provides loads of standard environments, Atari games, control tasks, robotics sims, lets everyone compare results apples to apples.
Makes sense. What else?
TensorFlow agents, or TF agents from
Hmm.
Google, it has solid production-ready implementations of algorithms like DQN, PPO, built on TensorFlow.
Production ready. Okay.
Stable baselines is another huge one, built on PyTorch. It's known for being really well documented, reliable, easy-to-use implementations of PPO, SAC, A3C, etc. Very popular.
Easy to use is always good.
Definitely. Then there's RLlib, built on Ray. Its focus is scalability training on multiple machines, handling really big problems.
Massive scale.
Yeah. And of course, PyTorch itself is super flexible if you want to build custom things. Google also has Dopamine, focused on fast prototyping, especially for value-based methods like DQN variants, and Keras RL integrates RL with the Keras API.
So a whole ecosystem, depending on your needs, benchmarking, production, ease of use, scale, custom research.
Pretty much, yeah. It's matured a lot.
Okay, zooming back out for a second. We talk about maximizing cumulative reward.
Yeah.
Can we restate the overall goals of RL? What is it fundamentally trying to achieve?
Right. The primary goal is always learning that optimal policy to get the maximum expected total reward over time. But that involves a few key things.
Like,
First, learning from interaction. No explicit labels telling it the right answer for each step. It learns from the consequences, the rewards.
luckily, learning by doing.
Second, balancing exploration versus exploitation. This is a huge one.
Trying new things versus sticking with what works.
Exactly. You have to explore to find potentially better strategies, but you also need to exploit what you already know to get reward. Finding the right balance is tricky.
Especially if rewards are
Oh yeah, sparse rewards make exploration really hard. And third, handling delayed rewards. An action taken now might only pay off or prove costly much later. The agent has to learn those long-term consequences.
connecting actions to distant outcomes.
Yep. And mathematically, this is all captured in that objective of maximizing the expected return, often using a discount factor, gamma, to weigh immediate rewards slightly higher than distant future ones.
Okay, so it's a quest for the best long-term strategy via interaction, exploration, and handling delays. But it's not all smooth sailing. What are the big challenges the field is still grappling with?
Oh, plenty. Sample efficiency is a major one.
Needing too much data.
Yeah, many algorithms need like millions or even billions of interactions to learn complex tasks. That's just not feasible in many real-world scenarios. Robots wear out, real-world experiments cost money.
So making them learn faster from less experience is key.
Huge area of research. That exploration-exploitation trade-off we mentioned, still really hard, especially when rewards are sparse or deceptive.
Finding that needle in a haystack.
Right. Credit assignment too, figuring out which specific actions in a long sequence were actually responsible for the final reward or failure.
Tricky.
Scalability is another ongoing issue. As state and action spaces get enormous, many algorithms just bog down computationally.
Handling complexity.
And generalization. You train an agent in simulation, does it work in the real world? Or even just a slightly different simulation. Making policies robust and adaptable is vital but difficult.
And then there are safety and ethical concerns.
Absolutely. If you specify the reward function badly, the agent might find unintended, potentially unsafe ways to maximize it, the reward hacking problem. Plus, issues of bias learned from data or environments, and interpretability. Why did the agent do that? Hard to trust a black box in high-stakes situations.
So lots of active research areas then: transfer learning, meta-learning, safe RL, interpretability.
Exactly. Trying to tackle all these limitations.
Okay, despite the challenges, where is RL making a real impact today? What are some standout applications?
We're seeing it deployed in quite a few places. Autonomous driving is a big one, using RL for things like path planning, control, making driving smoother and safer.
Optimizing the driving policy.
Yeah. Robotics is another huge area. Training robots for complex manipulation, grasping diverse objects, assembly tasks, also navigation in cluttered spaces, human-robot collaboration.
Moving beyond just repeating programmed motions.
Right, becoming more adaptive. Gaming, of course, has been a major testbed and showcase. AlphaGo beating the world Go champion was a landmark moment. And successes in chess, shogi, complex video games like Dota 2, StarCraft, showing RL can master incredibly complex strategies.
What about outside games and robots?
Recommendation systems are increasingly using RL. To personalize what content you see, articles, videos, products based on your interactions, trying to maximize engagement or whatever the platform's goal
So
is.
the feed is learning from my clicks.
Pretty much, yeah. Finance uses it too for things like algorithmic trading, optimizing investment portfolios, managing risk, though that's tricky due to market volatility and the need for safety.
High stakes.
Very. Healthcare is exploring RL for personalized treatment plans, adapting therapies based on patient response or optimizing resource allocation in hospitals. Still early days, huge safety considerations, obviously.
Makes sense.
Even natural language processing, using RL to fine-tune dialogue systems to be more engaging or helpful, or improve summarization and translation by treating text generation as a sequence of decisions.
That's broader than I realized. Didn't DeepMind use it for energy efficiency?
Oh, yeah, that was a big one. They used RL to control the cooling systems in Google's data centers, reportedly cutting the cooling energy bill significantly, like 40%.
Wow, that's tangible impact.
Definitely showed the potential for optimizing complex real-world systems.
What about more recent breakthroughs or directions mentioned in the reports? Anything cutting edge?
Yeah, there's exciting stuff happening. Progress on more generalist robot policies, robots that can understand and follow natural language instructions for a wider range of tasks.
Like pick up the red block.
Exactly, but getting much more sophisticated. There's also a lot of work integrating RL with large language models, LLMs, and world models.
How does that help?
LLMs can provide common sense, context, or help define reward functions. World models, as we discussed, help with planning and sample efficiency. It accelerates development.
Interesting synergy.
We're also seeing RL explored for code generation, trying to get AI to write code that adheres to specific, say, company coding styles.
Aligning with human standards.
Yeah, and that relates to RLHF reinforcement learning from human feedback. Using human preferences to guide the AI's learning, especially important for aligning large models like LLMs with human values. It's behind a lot of the recent chatbot improvement.
Ah, so that's where humans come back into the loop.
Exactly. Other areas mentioned include using RL in defense for automating high-risk tasks, in cybersecurity for detecting anomalies, optimizing agriculture,
Precision farming?
yeah, resource use, automation, precision healthcare again, optimizing complex treatments, more advanced dialogue systems, resilient supply chain optimization, smarter energy grids.
Eco-friendly power management?
Right. Multimodal learning for robots combining vision, touch, language. And a big underlying theme is just making RL more efficient, more customizable, and developing better ways to learn optimal policies, especially deterministic ones.
It really feels like the field is both broadening its applications and deepening its core capabilities.
It absolutely is. It's still challenging, but the progress is undeniable.
Okay, so let's try to wrap this up. Our deep dive suggests reinforcement learning is, well, a really powerful paradigm for learning through interaction to achieve goals.
Right, learning complex decision-making strategies.
We've seen its impact growing, from games and robotics to recommendations and even data center cooling.
And many more areas emerging.
But significant challenges remain. Sample efficiency, exploration, safety, generalization. These are still major research frontiers.
Absolutely. Lots of work still to be done to make it robust and truly widespread.
The progress with deep learning, algorithms like PPO and SAC, and integration with things like LLMs and human feedback, though, it shows the field is moving fast.
It's a very dynamic field, yes.
So as a final thought for our listeners,
Yeah.
thinking about your own world, your work, your field, what complex problem, what sequential decision-making process might be fundamentally changed if an agent could learn the optimal strategy just through interaction and reward?
That's a great question to ponder. Where could this learning approach make the biggest difference?
Something to think about. Thanks for joining us for this deep dive into reinforcement learning.